Alright, section 310 is about business and economic applications. Before we start, we have to define a few things, so we're going to figure out how to use calculus in the business world and how they use that today. So the marginal profit, we better define that. The rate of change of profit with respect to the number of units produced or sold. So how much profit we'll make by producing one extra unit for each additional extra unit. Marginal revenue, how much revenue we'll make for producing one extra or selling one extra unit. And marginal cost, how much it's going to cost us to produce one additional unit as well. Business terms and formulas that we need to know. X is the number of units produced or sold. P is the price per unit. A capital R is the total revenue from selling X units. The revenue would be then R equal to X times P. So the number of units that we sell times its price, that gives us our revenue. C, capital C, is the total cost for producing X units. C bar is the average cost per unit. So C bar equals our cost divided by X. So our total cost divided by our total number of units produced is going to give us our average cost. All right. And then our profit is going to be our revenue minus our cost. So whatever we make minus our cost. So say I make $2,000 selling t-shirts, but it cost me $1,000 to make them. My profit then is $1,000. The break-even point is the number of units for which our revenue equals our cost. So if it costs me $1,000 to make my t-shirts, all right, I'm going to have to, my break-even points is when I sell $1,000 worth of t-shirts. And so I didn't gain money, I didn't lose money. Called the break-even point. And lastly here, last thing to look at is we take the derivative of the revenue function. We'll get our marginal revenue, extra revenue for selling one additional unit. When we take the derivative of the cost function, we'll get our marginal cost, extra cost for producing one additional unit. Take the derivative of the profit function, we get marginal profit, extra profit from selling one additional unit. So we have an example here of a manufacturer determines that the profit derived from selling X units of a certain item is given by P equal to 0.002x cubed plus 10x. Find the marginal profit for the production level of 50 units. Well, we just found out that we can find the marginal profit by taking the derivative of the profit function. So let's go ahead and say dp dx is going to equal, let's take the derivative with respect to x. So 0.000, bring down my 3, so 6, x squared plus 10. And they want us to know what our marginal profit is when we have 50 units. So we just go ahead and we plug 50 units into our marginal profit formula. When I plug 50 units into there, I'm going to get $11.50. Then they want us to find the gain for, so B here, they want us to find a gain in profit by increasing production from 50 units to 51 units. So let's go ahead and look. All they want us to do is they want us to plug 50 into this equation. Then they want us to plug 51 into the profit equation as well. When I plug 50 units into that equation and multiply it all out on my calculator, I'm going to get $525.00. When I plug 51 units into my calculator and my profit function, I'm going to get $536.53. All right. So what happened? They want us to find our gain in profit. So from selling that one additional unit, we made $11.53, which is awfully close to what we just figured out in our marginal profit. So we're just showing you that the marginal profit, if we can take the derivative and figure that out like that, is very similar to just plugging it into our profit function in general. All right. Now the previous example, though, that example up there assumes that the extra production will not sell at the same price, or that will sell at the same price. But in the real world, we have what's called supply and demand. When the supply is high, the demand's pretty low because people can get their hands on it very easily. When the supply is very low, the demand is really high, and you can sell it for a lot more. A good example is gas. Right now, there's a shortage in gas, is what they say. So they're charging more per gallon of gas. It's gone up quite a bit. If we were to find some other oil field, I bet you that the price of gas would go down because we'd have more supply. All right, and so we have more supply, and people would be able to easily get their hands on it, so that people would have to charge less. So demand function is a number of units X that consumers are willing to purchase at a given price P per unit is defined as a function of X. So let's look at this example here. Business sells 2,000 items per month at a price of $10 each. It is predicted that monthly sales will increase by 250 items for each 25-cent reduction in price. Find the demand function corresponding to this prediction. So we want to write a demand function. Well, first of all, we know how much we sell, so we know how much we sell per month. So let's write an equation for how many units that we sell. So equation of X. We sell at least 2,000 per month, and then it'd be predicted that we will gain 250 units for every 25-cent reduction we have. Well, we need to write an equation right here. So every time we reduce our price, which is 10, by 25 cents, we're going to get another $250 kick. All right. So let's think about this a second. So if I reduce my price one time, I'd be at $9.75, and that would equal, whoops, 0.25, sorry, 0.25, all right, it'd equal 25 cents, right? Well, we want this equation here, so every time I reduce this, I want this equation inside here to equal 1, because every time I reduce it one time, all right, I want to gain 250 items sold. So if I do it one time, so I get $9.75. So if I subtract those two up top, all right, I get a difference of 25 cents. So that's one time. We want that inside equation to equal 1. Right now we're at 0.25. So what we can do to get this part to 1, we want it to equal 1 because every time we reduce it, we get 250 extra items sold. So what we can do is we can take that times 4, or we can divide by 1/4. All right, so that's a function, or that's our equation for X that relates our demand with our price. But we want to write our demand function. All right, so we want to get P by itself. So let's go ahead and simplify. We'll solve for P, our demand function. So we'll have 2,000 plus, if I distribute, I'll have 2,500 minus 250 P over 0.25, which is 1/4. So if I'm dividing by 1/4, I'm really multiplying by 4. So I can multiply each of these by 4. So I'd have 2,000 plus, let's see, 10,000 minus 250 times 4 would be 1,000 P, and that still equals X. Well, if we want to solve for our, equals X, sorry. If we want to solve for our demand function, then we get P by itself. So let's move our 10,000 P over to the other side. Well, no, let's combine 2,000 and 10,000 is 12,000. Let's move that to the other side. So now I have X minus 12,000 equal to a negative 1,000 P. All right, and to get P by itself, we'd divide by a negative 1,000. So I'm going to give, if I divide by a negative 1,000, I'll have 12 minus, so I divide by, that becomes a positive, minus a negative, so, or minus X all over 1,000. Okay, so there would be my demand function right there. Okay. So there's that example right there. Let's continue on. Example 3. It says a fast food restaurant has determined that monthly demand for its hamburgers is, their demand function equals 60,000 minus X all over 20,000. Find the increase in revenue per hamburger, the marginal revenue for monthly sales of 2,000 hamburgers. So first of all, we have to write an equation for total revenue. Okay, so to write that equation right there, we need to figure out, well, total revenue, R equals, if we go back up to our top, equals X times P. Well, we were given our P function right here. So our revenue is going to equal X times 60,000 minus x all over 20,000. All right, and I can distribute through, and I can probably pull pull our constant out to get our x's by themselves. So let's go 60,000 x minus x squared all over 20,000. Sorry, my smartboard's not working very well. It's not writing when I want it to. So there, so far, here's our revenue function. I think we can also pull a 20,000 out of there. If we pull a 20,000 out of there, well, let's just write it like this. Let's go 1 all over 20,000 equals 60,000 x minus x squared. Let's do that, and you'll find out why here in a little bit, because we're going to take the derivative of that. Okay, so far we have 1 all over 20,000 times 60,000 x minus x squared. To find the marginal revenue, we need to take the derivative of that, so let's rewrite that thing. Revenue equals 1 all over 20,000 times 60,000 x minus x squared. The reason where it's nice to pull out this 1 all over 20,000 is because we don't have to do the quotient rule. This way we can do the product rule. So the derivative of the first guy, this would be the first guy, would be 0, so it doesn't really matter. So we'd take the derivative of the first guy as 0, then we'd add it. So our dr dx, so then we'd take the derivative, so we'd have 0 plus then we leave our first guy, so 20,000 times the derivative of our second guy, which would be 60,000. Come on, smartboard. 60,000 minus 2x. So here is our dr dx equals 1 all over 20,000 times 60,000, minus 2x. All right, and the last thing they want us to do then is to evaluate x. So they want us to evaluate what our marginal revenue is for selling 200,000 hamburgers. So we're going to plug 200,000 hamburgers in there. So we plug 200,000 in for x. If I plug 200,000 here, I'm going to have 600,000, or sorry, 20,000. I'm sorry. The example said 20,000. I keep saying 200,000. If I plug 20,000 in, so I have 2 times 20,000, which would be 40,000. And I still have my 1 all over 20,000 out here. Okay, when I subtract inside my parentheses, I have 20,000. When I multiply by 1 all over 20,000, I end up getting 1. So inside here is 20,000. When I multiply it by here, 1 all over 20,000, I get 1. So what my marginal revenue for producing 20,000 units is $1. All right, it's $1 per unit. That's gonna have to be it for this. I'm running out of time for this video. Come back in the next video and we'll do a few more examples.